At 183 miles per hour, the experimental train roared down the tracks like nothing America had ever seen. But inside the control cabin, the engineers were about to discover something terrifying. The steel rails beneath them were beginning to buckle. The ties were splintering, and the ballast stones were literally exploding from the heat. What happened next would cost the New York Central Railroad millions of dollars and end one of the most ambitious experiments in American transportation history. This is the story of the M497 Black Beetle, the jet-powered train that was supposed to revolutionize rail travel, but instead became a cautionary tale about the dangers of pushing technology too far, too fast. To understand why anyone thought mounting jet engines on a train was a good idea, we need to go back to 1960s America. The country was in the middle of a transportation crisis that threatened to make railroads completely obsolete. By 1966, American railroads were dying. Not slowly, not gradually. They were hemorrhaging passengers at an alarming rate. Between 1945 and 1965, passenger rail traffic had dropped by nearly 84%. 84% in just 20 years. The reason was simple: highways and airlines. President Eisenhower's interstate highway system, begun in 1956, had created a network of smooth, fast roads that made automobile travel easier than ever before. And commercial aviation had exploded. Jets like the Boeing 707 could fly passengers from New York to Chicago in just 2 hours. Meanwhile, most American trains were still chugging along at 60 to 80 miles per hour, using technology that hadn't fundamentally changed since the 1920s. The writing was on the wall. Either railroads innovated or they died. The New York Central Railroad was feeling this pressure more than most. Once one of America's most prestigious railroads, the company was watching its passenger numbers collapse. Their flagship train, the 20th Century Limited, which had once been the height of luxury travel between New York and Chicago, was now running half empty. The railroad's president, Alfred Perlman, was desperate. He knew that incremental improvements wouldn't save them. They needed something dramatic, something revolutionary, something that would make headlines and prove that trains could still compete in the jet age. That's when Don Wetzel entered the picture. Wetzel was the vice president of engineering at New York Central, and he had a reputation as a creative problem solver. In early 1966, he gathered his team for a brainstorming session with one simple question: how could they make trains dramatically faster without spending millions on new locomotives? The solution they came up with was audacious, even by 1960 standards. If jet engines could make airplanes go 500 miles per hour, why couldn't they make trains go 150 or even 200 miles per hour? The idea wasn't entirely new. The French had experimented with jet-powered railcars in the 1950s, but those were small, experimental vehicles. What Wetzel was proposing was different. He wanted to take an existing passenger railcar, strap surplus military jet engines to it, and see just how fast they could make it go. The beauty of the plan was its simplicity and low cost. The U.S. military had thousands of surplus jet engines sitting in warehouses, left over from aircraft that had been retired or never built. New York Central could acquire these engines for practically nothing. The railcar they'd use was already sitting in their yards, an old Budd RDC-3 railcar from the 1950s. Total estimated cost, about $500,000. In contrast, developing a new high-speed train from scratch would cost tens of millions. On paper, it made perfect sense. In reality, they were about to create a monster. The railcar they selected for this experiment was number 497, a Budd rail diesel car built in 1956. It was already 10 years old, showing its age, but structurally sound. The RDC-3 was 85 feet long, weighed about 60 tons, and had been designed to carry mail and passengers on short-haul routes. It was never designed to break speed records. The jet engines they chose were General Electric J4719 turbojets. These were the same engines that powered the F-86 Sabre fighter jet during the Korean War. Each engine produced 5,200 pounds of thrust. They were going to mount 2 of them. That's 10,400 pounds of raw thrust, pushing a 60-ton railcar. To put that in perspective, most diesel locomotives of that era produced between 1,500 and 3,000 horsepower. These jet engines would be delivering thrust equivalent to roughly 7,000 horsepower. The modification work began in the winter of 1966 at the railroad's Collinwood shops in Cleveland, Ohio. The engineers faced immediate challenges. First, where exactly do you mount jet engines on a train? After considerable debate, they decided to mount both engines on top of the railcar, angled slightly upward. This served two purposes. First, it kept the engines away from the tracks and the flying debris that would inevitably be kicked up at high speeds. Second, the upward angle would theoretically create downforce, pressing the car harder onto the tracks. But this created its own problems. The railcar's roof had never been designed to support several tons of jet engines. The engineers had to reinforce the entire roof structure with steel beams and supports. They also had to ensure the aerodynamics wouldn't tear the car apart. Then came the fuel system. Jet engines are thirsty, very thirsty. The J-47 engines consumed fuel at a rate of about 1,000 gallons per hour at full throttle. The team installed massive fuel tanks inside the railcar, converting what had been the mail compartment into essentially a flying fuel depot on rails. Fire suppression systems were installed throughout the car. The engineers knew that a single fuel leak near engines running at 1,200 degrees Fahrenheit would be catastrophic. They installed multiple redundant systems, fire extinguishers, and emergency shutoff valves. The control cabin was modified to withstand the incredible noise. Even with soundproofing, the engineers knew the jet engines would be deafening. They equipped the operators with military-grade hearing protection, the same kind fighter pilots used. By March 1966, the M497, as it was now officially designated, was complete. It looked like something from a science fiction movie. The sleek silver railcar with two massive jet engines mounted on its roof like horns. The press immediately dubbed it the Black Beetle, due to its dark color scheme and insect-like appearance. But looking impressive and actually working were two very different things. On a cold morning in March 1966, the M497 made its first test run. The location was a straight section of track near Butler, Indiana. New York Central had closed this section to all other traffic. This wasn't just a safety precaution, it was a necessity. What they were about to do had never been attempted before. The test crew consisted of Don Wetzel himself, two experienced locomotive engineers, a mechanic, and a representative from General Electric. They were all volunteers. Everyone understood the risks. The first run was conservative by design. The engineers wanted to see how the rail car handled at conventional speeds before pushing it to its limits. They lit the jet engines with a sound that witnesses described as like standing next to a thunderstorm. The M497 rolled forward, conventional diesel engine providing initial momentum. Then, at about 40 miles per hour, they opened the jet throttles. The acceleration was immediate and violent. The rail car surged forward with a force that pressed everyone inside against their seats. Within seconds, they were traveling at 80 miles per hour, then 90, then 100. At 100 miles per hour, they shut down the jets. The first test was complete, and the rail car had performed flawlessly. The crew was ecstatic. They'd proven the basic concept worked. Over the next several weeks, they conducted more tests, gradually increasing the speed with each run. At 110 miles per hour, they noticed the first problems. The rail car began to vibrate, not dramatically, but enough to be concerning. The engineers suspected it was aerodynamic buffeting from the jet exhaust interacting with the car's structure. At 120 miles per hour, the vibration got worse, but the car remained stable and the track showed no signs of damage. They pressed on. At 130 miles per hour, something new happened. The engineers in the control cabin reported hearing unusual sounds from beneath the car, not mechanical sounds, environmental sounds. The ballast stones, the crushed rock that supports railroad ties, were being blown around by the jet exhaust. But here's what's important to understand. At these speeds, it wasn't just the forward thrust of the jets that was causing problems. It was the entire aerodynamic system they'd created. The jet exhaust was traveling at over 600 miles per hour.
When that superheated, supersonic exhaust hit the track behind the train, it created a cascade of effects the engineers hadn't fully anticipated. The heat alone was extraordinary. Jet exhaust exits the engine at approximately 1200 degrees Fahrenheit. Even though the engines were mounted on top of the car, enough of that heat was making it to the track bed to cause problems. The wooden railroad ties were beginning to char. The ballast stones, many of which had been there for decades, were being superheated and in some cases were literally exploding from thermal shock. But the team didn't know the full extent of this yet. They only saw that the car was performing well and they were achieving unprecedented speeds. So they made the decision to go for the record. On July 23, 1966, they prepared for the ultimate test. The goal was simple: push the M497 to its absolute maximum speed and see what American rail technology was truly capable of. The test section was a straight stretch of track near Bryan, Ohio. It was chosen because it had 26 miles of straight, level track with minimal curves. If they were going to break records, this was the place to do it. At 8 a.m., the M497 began its run. This time, they would hold nothing back. The jet engines roared to life, and the rail car began its acceleration. 80 miles per hour, 100 miles per hour, 120 miles per hour. The car was handling beautifully. Inside the cabin, the noise was incredible despite all the soundproofing. The engineers described it as sitting inside a continuous explosion. 140 miles per hour. At this speed, the landscape outside became a blur. Trees, buildings, road crossings, everything merged into a continuous stream of color and motion. The vibration that had concerned them at lower speeds had actually smoothed out. The car was riding on what felt like a cushion of air. Then they hit 160 miles per hour. At this speed, the M497 entered uncharted territory. No American train had ever traveled this fast on conventional tracks. The engineers in the cabin were monitoring every gauge, every indicator, looking for any sign of trouble. 170 miles per hour. The track ahead was straight and clear. The jet engines were running perfectly. Everything seemed to be going according to plan. Then they opened the throttles to maximum.
At 9:27 a.m. on July 23, 1966, the M497 Black Beetle reached its maximum recorded speed, 183.68 miles per hour. For exactly 15 seconds, it was the fastest train ever to run on American rails. Inside the cabin, the crew was jubilant. They'd done it. They'd proven that American railroads could compete with any high-speed system in the world. Don Wetzel radioed back to headquarters with the news. They began planning a press conference to announce their achievement. But as the M497 slowed down and eventually came to a stop, something became immediately apparent. Something was very, very wrong with the track. The maintenance crew that followed behind the test train reported the damage within hours, and it was far worse than anyone had imagined. For approximately 3 miles along the route where the M497 had reached its maximum speed, the track was devastated. The wooden railroad ties, which were supposed to last 20 to 30 years, were charred black. Many were split completely in half. The ballast, the crushed stone foundation, was scattered across a 30-foot wide path on either side of the tracks. In some places, the ballast had been blown away entirely, leaving the ties sitting directly on bare earth. But the most shocking discovery was the rails themselves. At multiple points along the 3-mile stretch, the steel rails showed signs of heat damage. The molecular structure of the steel had been altered by the extreme temperatures. In railroad terminology, the rails had been thermally stressed. They would need to be replaced. The estimated damage? $2.3 million in 1966 dollars. That's approximately $21 million in today's money. For context, the entire M497 project had cost about $500,000. A single 15-second run at maximum speed had caused damage worth nearly 5 times the project's entire budget. What had happened? The engineers began a comprehensive analysis, and what they discovered fundamentally changed their understanding of high-speed rail physics. The problem wasn't just the heat, though that was significant.
The real issue was the complex interaction between the jet exhaust, the track structure, and the aerodynamics of the moving train. At speeds above 150 miles per hour, the M497 was creating what engineers call a pressure wave. This wave traveled both ahead and behind the train, and it was powerful enough to lift small objects, including ballast stones, off the ground. When combined with the hurricane-force winds from the jet exhaust, these stones became projectiles, hammering the sides of the railcar and damaging the track infrastructure. The jet exhaust itself was creating a phenomenon similar to a blowtorch effect. Even though the engines were mounted on top of the car, the exhaust was being deflected downward by the car's aerodynamic wake. This meant that superheated, high-velocity gases were being directed straight at the track bed. The wooden ties never had a chance. Wood begins to char at around 350 degrees Fahrenheit. The jet exhaust was delivering sustained temperatures well over 1,000 degrees. The ties weren't just being heated, they were being actively cooked, losing structural integrity with every second of exposure. The ballast stones were experiencing thermal shock. These stones had been buried in the track bed for years, maintaining a relatively constant temperature. Suddenly, they were being hit with temperatures hot enough to melt lead. The rapid heating caused the stones to expand faster than their molecular structure could handle. Many simply shattered. And then there was the issue of the rails themselves. Railroad steel is incredibly strong, but it's also precisely engineered to maintain its properties within a specific temperature range. The thermal stress from the jet exhaust was causing the rails to expand and contract rapidly, creating microfractures in the steel. Over time, these fractures would have led to catastrophic rail failure. The New York Central Railroad faced a difficult decision. They'd achieved something remarkable. They'd proven that extreme speeds were possible on conventional rail infrastructure. But at what cost?
The immediate question facing New York Central's board of directors was straightforward. Could the M497 be modified to solve these problems? The engineering team went back to the drawing board. They proposed several solutions. They could angle the jet engines differently to direct the exhaust away from the tracks. They could install heat shields and deflectors. They could even reduce the power output to achieve slightly lower speeds with less infrastructure damage. But every solution had a fundamental problem. The entire appeal of the M497 was its speed. If they had to slow it down to prevent track damage, what was the point? A 120-mile-per-hour train wasn't revolutionary. Diesel-electric locomotives were already approaching those speeds with far less complexity and cost. Then came the financial reality check. The track damage from a single high-speed run cost $2.3 million. If they actually put the M497 into regular service, running it even once a day would require constant track maintenance and replacement. The operating costs would be astronomical. There was also the issue of practicality. The M497 had been tested on straight, level track in ideal conditions, but real-world rail service meant curves, switches, grade crossings, and stations. The jet engines couldn't be throttled quickly enough for normal railroad operations. The fuel consumption made it economically unviable. And perhaps most importantly, the noise was absolutely intolerable for anything other than brief test runs in isolated areas. Residents near the test track in Bryan, Ohio, had already filed dozens of noise complaints. The sound of the M497 at full throttle could be heard over 10 miles away. Witnesses described it as louder than a military airbase. Windows rattled in homes 3 miles from the tracks. One farmer reported that his chickens stopped laying eggs for a week after the test run. By September 1966, just 2 months after the record-breaking run, New York Central quietly announced that the M497 project was being indefinitely postponed. This was corporate speak for canceled. Don Wetzel and his team were disappointed but not surprised. They'd achieved their goal of proving high-speed rail was possible on American tracks, but they'd also proven that jet propulsion was not the answer. The M497 made a few more test runs at lower speeds over the following months, mostly for publicity purposes and to gather additional data, but it never again reached anywhere near its maximum speed. The risk of track damage was simply too great. In 1968, the jet engines were removed. The M497 was stripped of its experimental equipment and converted back to a conventional maintenance vehicle.
It spent the next decade performing mundane tasks, hauling equipment and supplies around the railroad's maintenance facilities. In 1977, the car was finally retired and scrapped. Today, only photographs and film footage remain as evidence that the Black Beetle ever existed. But here's what's important to understand. The M497 wasn't really a failure. It was an extremely successful experiment that produced a negative result. The project definitively proved that jet propulsion was not a viable solution for high-speed rail. This saved countless other railroads from wasting money on similar experiments. The data collected from the M497's test runs contributed to understanding track dynamics at high speeds, information that would later be used in the development of legitimate high-speed rail systems. The lessons learned from the M497 directly influenced the development of Amtrak's Acela Express, which began service in 2000. The Acela uses conventional electric propulsion and can reach speeds of 150 miles per hour. Not as fast as the M497's record, but fast enough to be practical and sustainable. The track damage issue that plagued the M497 led to innovations in track design and maintenance. Modern high-speed rail systems use continuously welded rails, concrete ties, and specially designed ballast that can withstand the stresses of high-speed operation. The aerodynamic problems identified during the M497 tests influenced the design of future high-speed trains. Engineers learned that simply making a train go fast wasn't enough. The entire system, the train, the tracks, and the supporting infrastructure had to be designed as an integrated whole.
The story of the M497 raises an interesting question. Why did American railroads abandon high-speed rail development for decades after this experiment? The answer is complex, but it largely comes down to economics and politics. By the late 1960s, it was clear that passenger rail in America was dying. The highways and airlines had won. Rather than invest billions in unproven high-speed rail technology, most railroads chose to focus on freight service, which remained profitable. The federal government wasn't willing to provide the massive subsidies that would have been necessary to build a true high-speed rail network. In contrast, countries like Japan and France made high-speed rail a national priority, investing billions in infrastructure development. Japan's Shinkansen bullet train began service in 1964, 2 years before the M497's record run. The Japanese took a completely different approach. Instead of trying to adapt existing infrastructure, they built an entirely new rail network from scratch, designed specifically for high-speed operation. The original Shinkansen trains traveled at 130 miles per hour, slower than the M497, but they did it safely, reliably, and without destroying the tracks. By the time American engineers were struggling with jet-powered trains and melted tracks, Japan was already operating a successful high-speed rail system that carried millions of passengers every year. The French followed a similar path with their TGV system in the 1970s. Like the Japanese, they understood that high-speed rail required purpose-built infrastructure. You couldn't just take existing tracks and run trains faster. You needed to design everything, the trains, the tracks, the signals, the stations, as an integrated system. The M497 represented a very American approach to the problem, innovative, ambitious, and pragmatic. Take what you have, modify it creatively, and see what happens. In many ways, this approach has served American engineering well, but for high-speed rail, it simply didn't work. There's an interesting postscript to the story. In the 1990s, as high-speed rail was finally being reconsidered in America, researchers went back and studied the M497 data. What they found was fascinating. The M497 had actually been aerodynamically efficient for its era. The jet engines, despite their problems, had proven that speeds above 180 miles per hour were physically possible on conventional tracks. The track damage wasn't inevitable. It was the result of specific design choices, primarily the downward deflection of the jet exhaust. This led some engineers to wonder, what if they'd used different engines? What if they'd mounted them differently? What if they'd built the entire system from scratch instead of adapting an existing railcar? These what-if questions spawned a series of computer simulations in the late 1990s.
Researchers modeled various configurations of jet-powered trains, testing them virtually against modern track standards. The results were surprising. With modern materials, better aerodynamics, and purpose-built infrastructure, a jet-powered train could theoretically operate at speeds above 200 miles per hour without causing significant track damage. But by this point, the technology had been superseded. Modern high-speed trains use electric motors and achieve similar or better speeds with far greater efficiency, lower operating costs, and minimal infrastructure damage. The jet train's moment had passed.
The M497 Black Beetle holds a unique place in American transportation history. For 15 glorious seconds on July 23, 1966, it was the fastest train in America. It proved that extraordinary speeds were possible. It demonstrated American engineering ingenuity and willingness to take risks. But it also taught us a harder lesson, that innovation without sustainability is just spectacle. Speed for speed's sake accomplishes nothing if it destroys the very infrastructure it depends on. The 3 miles of melted, shattered, and ruined track left in the M497's wake became a metaphor for a certain kind of American ambition. The desire to be first, to be fastest, to achieve the impossible sometimes blinds us to the practical realities of actually making something work. Don Wetzel and his team weren't wrong to try. In fact, their willingness to experiment, to push boundaries, to literally strap jet engines to a train and see what happened, represents the best of American engineering culture. We need people willing to ask what if and then actually find out. But we also need people willing to ask at what cost and is there a better way? The true legacy of the M497 isn't its speed record, which was eventually broken by other American trains using conventional propulsion. It's not even the technical data it generated, though that was valuable. The real legacy is the lesson it taught about the difference between doing something spectacular and doing something right. Today, as America finally begins to seriously invest in high-speed rail, we're following the path blazed by Japan and France decades ago. We're building purpose-designed infrastructure. We're using proven electric propulsion technology. We're planning for sustainability and long-term operation, not just record-breaking test runs. It took us 60 years to learn what the M497 tried to teach us in a single afternoon. Sometimes the fastest way forward is not the straightest path. Sometimes the most spectacular solution is not the right one. And sometimes you need to melt a few miles of railroad track to learn these lessons. The M497 Black Beetle flew across the American countryside for 15 seconds at 183 miles per hour. In that brief moment, it represented everything Americans wanted to believe about their technological prowess and innovative spirit. But the 3 miles of devastated track it left behind told a different story. A story about the price of ambition unchecked by practicality. A story that American railroads would spend the next half-century learning to understand. Thank you for watching Iron Chronicles. If you found this story fascinating, please like and subscribe. We'll be bringing you more stories of engineering ambition, spectacular failures, and the hard lessons learned when humans push technology to its absolute limits. Until next time, remember, not every innovation that succeeds technically succeeds practically. And sometimes the most valuable discoveries are the ones that teach us what not to do.